Uh, can you please confirm whether am I audible or not? Just by raising your hand or writing yes in the chat box. So we'll wait for another 2 minutes, and when the people will join, we can start. Okay, I think people will join in some time, so we can start now. First of all, welcome you all to the problem solving session for the second week. So today my goal is to basically assist you solving some problems similar to your week 2 assignment. So what I am going to do, as like last session, I will take a few problems which have usually one key concept behind them, and I will mainly focus on the concept so that using the same concept you can solve the assignment problems. So that is pretty much my goal, and feel please feel free to stop me anytime if you are unable to understand what I'm explaining, or you think I'm making some mistake. Please stop then also. It would I'd really appreciate that. And okay, with that note, let's begin. So today's first problem that we are going to discuss is about the autocorrelation function. So Professor Aditya already have explained in an excellent manner and very detailed discussion about what autocorrelation function is. I would just like to replicate a few things from there. So let me begin. Basically the question asked here that you are given a signal and its autocorrelation function is defined as this. So basically you have to compute your autocorrelation function. So let me write down the mathematical expression for autocorrelation function first, then we will intuitively see that what does it exactly signify apart from the mathematical formula, because the formulas are easy to forget, but once you understand the concept behind them you will be able to appreciate it better. So autocorrelation function is given as follows: for a signal x, rx tau is equal to minus infinity to infinity x t x t minus tau dt. So this is what autocorrelation function is. This is the formula. So what does it signify? It signifies the degree of self similarity of a signal for a lag tau. So what does I exactly mean by that? So basically you have a signal xt and then you pick the shifted version of the signal. It may be lagging, it may be leading. By the way, when I say here lag tau, that basically can go in both direction. The version of xt can be leading or it can be lagging. So let's pick the signal in the example, which is xt e to the power minus t ut. So if I want to draw the representation of the signal, what it's going to be? So this is a unit step function. I guess you already know that unit step function has this property that u of t is equal to 1 for t 0 onwards and it takes value 0 otherwise. So if I like to draw the representation of ut here, that would come out to be something like this. So e to the power minus t at is pretty straightforward. Sorry, ut, its representation is going to be as follows. Anyway, we need not care about the negative axis because ut is 0 there, so only thing you care about here, and this is a exponential. More importantly, it is decreasing exponential. So this is what e to the power minus t ut is. Now when we say that we need to find its autocorrelation function, so what we basically need to do here, we need to pick a shifted version of this signal. So what do I exactly mean by that? Let's consider this lag tau. We first consider the easy case where tau is greater than 0. So what is x t minus tau going to look like? It's e to the power minus t minus tau u t minus tau. Now look at this unit step here. Now it starts instead of starting from 0, it will start from tau, right? Because if t is less than tau, let me write it down, u t minus tau is equal to 1 for t greater than equal to tau and 0 otherwise. This is because if t is less than tau, then this term inside is going to be negative and unit step will produce 0 for that. So let me write down the shifted version on top of this only with a different color. So this one is here, e to the power minus t minus tau u t minus tau, and this point here is tau itself. We already considered that we are focusing on the case when tau is greater than 0. And this one here is e to the power minus t ut. So now you see this integral here as per the definition of autocorrelation function. If we write here, let me write here minus infinity to infinity e to the power minus t ut e to the power minus t minus tau u t minus tau dt. See, as of now, even if we don't consider about this exponential terms, we just pick these two, unit function ut and shifted version of that unit step function u t minus tau. So you can see this product is non-zero only when t is greater than tau. So this range here, this is an integral over t, and this range here runs from minus infinity to infinity. But we can see the function itself contain the unit step function and the shifted version of it. So this product ut and ut minus tau is only non-zero when t greater than tau. Let me show that by different color here. So this one here, yes, can you please mute yourself? Okay, thank you. So what I was saying, this is what unit step function is, and this one I'm currently drawing is a shifted version of unit step function that starts from tau. So you can see if I take the multiplication of this with this, so this is only going to be non-zero in this region for t values greater than tau. This entire range, that is less than tau up to minus infinity, this multiplication is going to result into 0. So here my integral limit is going to change when we consider tau greater than equal to 0. So let me introduce a slide here. So we have this integral that is minus infinity to infinity e to the power minus e to the power minus t ut e to the power minus t minus tau u t minus tau dt. But we already seen that ut into ut minus tau is only going to be 1 when t greater than equal to tau and 0 otherwise. So the integral here we can change it to tau onwards to infinity, because for uh, something less than minus infinity to tau, this function is going to be 0, and if you are integrating 0 over the interval, it is going to produce nothing but 0 only. So our effective integration limit should be tau onwards to infinity. So now we have e to the power minus t. Now we can remove these two because the product is going to be 1, and here we have e to the power minus t minus tau dt. So see here, tau here is greater than 0 we assume, but that is a constant, that is the denotes what lag we want to consider, but that is constant with respect to the variable t here, so you can take that outside. So we'll have e to the power tau outside. Here we have tau to infinity e to the power minus 2t dt, and if we compute the integral, what we will get, e to the power tau 1 over 2 minus sign here, e to the power minus 2t tau up to infinity. So we'll have minus e to the power tau by 2, to replace infinity in place of t, e to the power minus infinity, that is 0, minus e to the power minus 2 tau minus 2 tau. So what will obtain, e to the power minus tau by 2. Now remember, the answer doesn't end here, because we only consider the case when tau is greater than equal to 0. So effectively the signal is leading. So next we will consider the case when tau is negative. Sorry, this is not the leading case, this is actually lagging, it's lagging by a tau. Now when tau is negative, that is the next case we are considering, this is actually leading action. So in this case you will have unit function as it is, that starts from 0, but the leading version of unit step function will start somewhere from here, and it will move onwards. So basically you will have, this is ut, and this one is here ut plus tau, and it starts from minus tau. So let us compute the autocorrelation function in this case, minus infinity to infinity e to the power minus t ut e to the power minus t minus tau u t minus tau, sorry, t plus tau dt. Now in this case you see that this product here ut and ut plus tau is non-zero only when t is greater than equal to 0, and it's 0 otherwise, because this particular region they are both 1, so this is going to matter. Anything less than t anything less than 0, this product here is going to be 0. So now our modified integration limit, we can write it as 0 to infinity, and we have e to the power minus t, e to the power minus t plus tau dt. Tau is again a constant, so we can take e to the power minus tau outside. So as previous, we'll end up with minus 1 over 2 e to the power minus 2t limit 0 to infinity. What we will get? Minus e to the power minus tau over 2 here. We'll have infinity in place of t, so 0, and here in place of t we'll have 1, so it's 1. So here we have e to the power minus tau over 2. So let me introduce one more slide here. I think I did the calculation right. Yes. Yeah. So for tau positive, that is the lagging case, we have Rx tau is equal to 1 over 2 e to the power minus tau, and for tau less than equal to 0, that is the leading case, we also have Rx tau is equal to 1 over 2 e to the power minus tau. Okay, I guess I made here some mistake. It's tau greater than equal to 0 here. This is lagging, and okay, this is a mistake I made here. This should not be minus tau. This is tau only, because we already consider tau to be negative, so it's fine there. And this sign should not change, they should remain as it is, because the tau being considered negative, that is already been taken care of. Sorry for this mistake. So I hope I was able to make you understand what I did wrong here. So this will remain ut minus tau only, but only thing is tau is negative itself, so it will start from here. So everything will be same as before. It will be t minus tau, should be positive here. Yes, now it's fine. So we'll end up having, here we'll have e to the power tau. So we can see that when tau is positive, that is the lagging case, here we'll have autocorrelation function 1 over 2 e to the power minus tau. When tau is negative, that is the leading case which corresponds to this, we'll have rx tau is equal to 1 over 2 e to the power tau. So if I would like to write in a compact notation, what I can do, you can write rx tau is equal to 1 over 2 e to the power minus absolute value of tau. And how you can do that? Because you see, tau, when tau is positive, absolute value of tau is nothing but the tau only, so you can just remove the absolute sign and you will obtain 1 over 2 e to the power minus tau. Now when tau is negative, absolute value of tau is actually negative of tau. So when you replace here, so let me write it down, tau negative means absolute value of tau is equal to minus tau. So you can replace here, minus absolute value of tau is nothing but tau. So these two things can be compactly written in this manner. So your autocorrelation function have expression like this, and if you would like to draw that, so basically you will see the decreasing exponential on both side of time axis, both positive and negative. At this point it will have a value of 1 over 2, and this is the graph of 1 over 2 to the power minus tau. So the answer is this one, second. I guess this autocorrelation function explanation is pretty clear to all of you. With that, let us proceed to our next question. Okay, so xf denotes the Fourier transform of the signal xt. So what should be the Fourier transform of the signal xt to the power minus e to the power j 2 pi fct. So what does it mean by multiplying xt with this? First of all, this is what this term is. Can one of you please volunteer here and tell me what this term represent? So basically in time domain, I am multiplying the signal xt with e to the power j 2 by fct, and what is it usually called? I'm assuming you have gone through the lecture, so you might have multiple times that this has a special name. This signal has a special name. So what is that? Any one of you? Okay, this one is nothing but a complex sinusoid. So basically what you are doing, you are multiplying signal with a complex sinusoid in time domain. So when you talk about Fourier transform, it's inevitably in frequency domain we are talking about. So when you multiply a signal with a complex sinusoid in time domain, what do you expect will happen in frequency domain? Frequency domain. So xt is the time domain representation, xf is its Fourier transform representation. So far so good. Now you multiply xt with a complex sinusoid in time domain. So what change you really expect to happen in frequency domain? What will happen to the spectrum of the signal xt? So let us try to see that from a little bit fundamental perspective from the Fourier transform itself. So that is, you obtain the Fourier transform by what? You have xt e to the power minus j 2 pi ft dt. You compute the integral from minus infinity to infinity. This integral is over t, and this whole thing is a function of f. So you obtain Fourier transform by that. So let's assume now in place of xt you are willing to have the Fourier transform of xt times e to the power j 2 pi f c t. So this is now your whole function. The rest of the part will remain intact, e to the power j 2 pi f t dt. Now you can see there are two exponential, one here, one here. So we can easily combine them, minus infinity to infinity xt e to the power j 2 pi, we take a minus here, f minus f c t dt. This is what we are obtaining. Okay, by the way, this is not equal to xf, so that's a wrong notation. It should not be. I'm computing it in independent manner. So now I can write it as minus infinity to infinity xt e to the power minus j 2 pi. By change of variable I am denoting f minus fc as f dash. It is 2 pi f dash t dt. So of course the answer is going to be x of f dash. Now how this f dash and f are related, you can see from this change of variable here only, right? So f dash is nothing but f minus fc. So what we are getting here is nothing but x of f minus fc. So this is all about math. So when you obtain the Fourier transform of xt times e to the power j 2 pi fct as x of f minus fc. But what is the key message behind it? What is happening in frequency domain? So when you are multiplying the signal with a complex sinusoid in time domain, you are essentially shifting the spectrum of x. And what is the shift amount? Shift amount is the frequency of the complex sinusoid. So as far as the answer is concerned, it's going to be 3. But I would like to point out one more key point here. So let's introduce a slide. So when we multiply a signal with a complex sinusoid of frequency fc in frequency domain, we essentially shift the original spectrum of original signal by fc. So if we want to see in a geometric way, so let's consider this is your xt. I'm just drawing some hypothetical kind of figures. They need not to be exactly true. So this is maybe your time domain signal, a pulse kind of thing. So in frequency domain, what you are having is this. This is your frequency domain representation. This is xt and this is xf. So when you multiply this with a complex sinusoid e to the power j 2 pi fct, what is basically going to happen in frequency domain, the spectrum shape will remain unchanged but they will be shifted. For example, here we have assumed that the spectrum is centered around 0 frequency. Now it will be shifted in both positive and negative axis to the center frequency fc here and center frequency minus fc here. So that is the effect you will see when you multiply a signal with a complex sinusoid. Frequency domain, its spectrum shifted. And what is the significance of the spectrum? Now because earlier your power, let's say, is concentrated around the 0 frequency, maybe your the entire signal power lies in this frequency range, but the moment you multiply with a um, complex sinusoid, there is no power actually remains here. Your entire power is shifted in this band here at center frequency fc, not at 0. So that is the message I would like to deliver here, that that's exactly what happens beyond mathematics between the time and frequency domain representation. So let us move to our third question here. This one is pretty easy actually. So you have a system which is said to be time invariant and you are feeding the system with the input xt which gives output yt. So if the system is time invariant and you feed some delayed version of the signal, that is xt minus t naught, that is it delayed by t naught, can you guess the corresponding output from yt, like whether you will see the similar delayed output or not? So actually what happened, that is pretty straightforward. This is your system, you are calling it time invariant. Now the good thing about the time invariant systems are, suppose you are feeding input at any time, let's say xt, and you observe the output yt. The good thing about that, if you send some delayed version of the signal t minus t naught, then by definition of time invariant system, what you are going to observe is the same delayed version of output. That is the itself the definition of time invariant system. So if you feed the delayed version of the input, you will obtain the same delayed version of the output, and that is only possible for time invariant system. But in practical, if the system is time variant, what does that mean? That here also you feed xt and you obtain yt, but feeding x minus x of t minus t naught doesn't guarantee that you will obtain yt minus t naught, because in time variant system that is not possible. But if your system is time invariant and you are giving the delayed version of input, it will produce the exact delayed version of output. For example, here the answer is going to be yt minus t naught. That was pretty straightforward. So here we need to talk about I think when you went through the lectures of week 2 and week 1 also to some extent, one kind of signal relationship between time and frequency domain has been highlighted multiple times, that is the pulse kind. So in the examples actually you have seen that if you have a pulse signal in time domain, that would lead to a sinc function in frequency domain. This is frequency domain, this is time domain. So basically let us try to derive first that let's start with a time domain signal xt, which takes value 1 here from minus t by 2 to t by 2. So you enter with this kind of t. This is 1 for absolute value of t less than equal to t by 2 and 0 otherwise. So it's a time limited signal basically, and aperiodic of course, because there is no repetition, it is a time limited and it is limited only this time duration of t. So we are supposed to find the Fourier transform of this signal. And how do you do that? We have xf expression as xt e to the power minus j 2 pi ft dt integral minus infinity to infinity but xt is only valid from minus t by 2 to t by 2, right? So we have minus t by 2 e to the power minus j 2 pi ft dt, and it is given as 1 over minus j 2 pi f to the power minus j 2 pi ft when t is evaluated at minus t by 2 and t by 2, minus j 2 pi f a to the power minus j, we replace t by 2 in place of t here, we'll obtain pi f t minus a to the power j pi f t. So let me introduce a new slide here. A to the power minus j pi f t we have, and minus basically the difference between two complex sinusoid, so minus here a f t. Now we know that sine x is equal to e to the power x minus e to the power minus x, sorry, e to the power ix e to the power minus ix by 2i. Of course here it's 2j, so it's let's denote the complex number as j here. So if we use this here, so basically this term actually translate to minus 2j sine pi f t. So what we obtain as the Fourier transform, we already have 1 over minus 2j pi f, and here we have minus 2j sine pi f t. Now this minus 2j cancels, we are left with sine of pi f t by pi f. If you want to write it in terms of sinc function, we need to have a t outside, so that we have sine pi f t by pi f t and t sinc ft, where sinc function we have seen have following expression: sine of pi x by pi x. And what are its characteristics? It follows the similar behavior to sine function. The only difference is its amplitude. Unlike sine function, amplitude goes down with x. So sinc function basically shows the similar behavior with sine function only, but unlike sine function, its amplitude also goes down as x increases. So we have a pulse signal in time domain minus t by, this is 1, sorry, minus t by 2 here, t by 2 here, and we have corresponding Fourier transform as sinc function t sinc f t. Now we have seen already in lecture multiple times and also in our previous problem solving session that if x t has a Fourier transform xf, the duality says that x of t will have Fourier transform representation small x of minus f. But here it's symmetric, so x of minus f and x of f are same. So now let us move to our question here. So you see, now we have a signal sinc 4t. So let's denote this signal as a pulse signal of with t pt, right? So let me introduce a slide here. So we have seen that pt of unit magnitude has a Fourier transform of t sinc f t, right? Now this is what xf is. Now I want to get xt from it. What I need to do, I will have b sinc bt, where b corresponds to the bandwidth. And there only I will have this pulse of b will have a pulse of with b minus b by 2 to b by 2 of unit amplitude. So if we compare with the expression here, that is sinc 4t, let us consider. So we have sinc 4t. So that says my bandwidth part is going to be minus b by 2, that is minus 4 by 2 to 4 by 2, that is minus 2 to 2. So my function frequency pulse in the frequency domain is non-zero for norm of f, absolute value of f less than equal to 2. But what about amplitude? This pulse is supposed to have unit amplitude if we have 4 here also, but there is no 4 here. So both sides need to be divided by b. So what we'll have 1 over 4 p 4 of f. So this amplitude here is going to be 1 over 4 for this function. Had it been 4 here, then we'll have unit amplitude, but since there is no 4, in time domain we have sinc 4t, sinc function, and the corresponding frequency domain representation comes out to be 1 over 4, a pulse of width 4 and amplitude of 1 over 4. So basically the frequency domain representation frequency domain representation is given as 1 over 4 whenever absolute value of f is less than equal to 2 and 0 outside this range. So let us check which of the answer matches. 1 over 2 for 1 4 5 2 1 yep, this one here is the correct one. So let us move to our next question. It is said we are given a complex signal xt and what its energy is going to be. So we have xt as 2 over 1 plus j 2t. So how do you exactly compute energy of a signal? Anyone would like to say anything about this? How should I proceed? Okay, so when it comes to computing energy of this signal x, what you need to do, simply you need to integrate the absolute value square of xt from minus infinity to infinity. That's how you compute the expectation. So what your this is going to be norm of absolute value of xt square. How do you compute it? You have xt, it's a complex signal, so multiply it with complex conjugate of xt. And how do you get it? 2 over 1 plus j 2t into complex conjugate of this 1 plus j 2t. And this, how we can write it? We can multiply in bottom by 1 minus j. Okay, let me write it here. 2 over 1 plus j 2t. So what we can do, we multiply the numerator denominator with 1 minus j 2t. So here we have 1 plus j 2t, 1 minus j 2t. So what we will left with, here we will have a square minus b square, 1 minus j square, so j square is minus 1, so minus 1 is plus 2t whole square, that is 4t square. So what its conjugate is going to be 2 plus 1 plus j 2t, conjugate is going to be 2 into 1 plus j 2t divided by 1 plus 4t square. So you replace the value here, but you will see that absolute value of xt square is nothing but 4 divided by 1 plus 4t square. Okay, next you have to compute the the integral here, minus infinity to infinity 4 over 1 plus 4t square dt. So let us compute the integral here, minus infinity to infinity 4 over 1 plus 4t square dt. Here what I am doing, here I will make a change of variable, that is we are taking t dash is equal to 2t. Okay, so what we will have, we take 2 common outside, then we have 2 dt, that is basically minus infinity to infinity 1 over 1 plus 2t whole square d of 2t, and we make the change of variable here. So we'll obtain 2 into minus infinity to infinity 1 over 1 plus t dash square dt dash. So this will, the integral is in standard form of tan inverse of t dash, and it runs from minus infinity to infinity. So what you are going to obtain here, pi by 2 minus of pi by 2, sorry, minus of minus pi by 2. So this is pi, you will have 2 pi here. So the energy being computed here is same as 2 pi. This is the crude way, but if we try to go through the autocorrelation route, is there any simpler way you can compute that? Let's see the expression here, 2 over 1 plus j 2t. So let me write it down. Two over 1 plus j 2t. If we consider e to the power minus at, what its Fourier transform is going to be, e to the power minus at ut. Its Fourier transform, let's compute. 1 over a plus j 2 pi f. So if we have e to the power minus t ut, we'll have 1 over 1 plus j 2 pi f. Let us just make e to the power minus pi t, then we'll have pi times 1 plus this. So basically if I have e to the power minus pi t ut times pi, I will have this Fourier transform 1 over 1 plus j 2 f. So this is xt, this is xf. Now if I compute xt, what I will have 1 over 1 plus j 2t, which have this Fourier transform pi e to the power minus pi f uf, right? U of minus f and pi f. Yeah, it's correct now. So Parseval theorem tells us Parseval theorem for continuous signal. What does it say? That energy of the signal can be represented in both time and frequency domain, and they are equal only. What I mean by that, absolute value of xt square dt is equal to minus infinity to infinity x of f absolute value square df. And how did we obtain reach here? So you might remember that Rx, that is the autocorrelation function tau, is obtained as x infinity to infinity x t minus tau x star t minus tau dt, right? And we have also seen that Rx tau, the frequency domain, like the Fourier transform autocorrelation function, is given as sf f, which is absolute value of xf square. This term here is called energy spectral density. So this expression of Rx tau we already have. So now in place of tau, if we replace tau is equal to 0, what we will obtain? Rx of 0 is equal to minus infinity to infinity xt x star of t dt, and this is nothing but absolute value square of xt, which is energy of the signal. On the similar note, this is the Fourier transform. This is the Fourier transform. So if I am interested in the inverse Fourier transform, that is the we want to obtain Rx tau from Sxf. How will we obtain that? We need to integrate Sxf e to the power j 2 pi ft f tau df. Now if we make the tau is equal to 0 here also, what we will obtain? Rx 0 is equal to minus infinity to infinity Sxf df, and we have already seen this Sxf is nothing but absolute value of xf square df. So this is another equality of correlation when the lag is 0, and we obtain the expression of Rx0 already in terms of time domain representation. So that basically means 1 and 2 are same, that it doesn't matter whether you compute energy in the time domain or you compute energy in terms of your spectra, that is frequency domain, the energy is going to be same only, and they are equal. So with these things in mind, let us see what we obtained here. That is 1 plus j 2t is given as this expression here. So let me introduce a new slide here. We obtain 1 plus j 2t. Fourier transform we obtain as pi a to the power pi f u, inverse of unit step function. So how can we obtain the power of this energy of this from the Fourier transform? We just need to, this energy here can be obtained by integrating, this is let's say x of f, we have to integrate the absolute value of xf over the entire spectra, that is minus infinity to infinity. And what we have here is pi to the power pi f, so let's write it minus infinity to infinity pi square e to the power 2 pi f df, okay, u of minus f. So this integral is valid from, since it's minus f, minus infinity to 0, pi square would be outside, e to the power 2 pi f df, and here we'll have pi square divided by 2 pi e to the power 2 pi f minus infinity and 0. So we are having pi by 2 and here we are obtaining 1 minus 0. So here we are obtaining the expression of energy as pi by 2. Most likely I did some mistake at some place here. The question is where. I tried to compute this here. Okay, 2 over this comes out to be, okay, 2 here dt d dash, fine, pi by 2 . t. Okay, this seems correct, so most likely here in the frequency transform I make some error. Just let me compute the e to the power minus at ut, the Fourier transform of that. E to the power minus at to the power minus j 2 pi ft dt minus infinity to infinity. So we'll have 1 over a plus j 2 pi f minus, of course, e to the power minus a plus j 2 pi f t dt 0 to infinity t here, a plus j 2 pi f e to the power minus a outside over j 2 pi minus 2 pi f t j 2 pi f t 0 to infinity. It will have 0 minus 1, have e to the power minus a by j 2 pi f. Okay, I guess I made some mistake here in the alternative part, the second thing I tried, so please ignore this part. This one here is fine, but yeah, ignore this part. I'll try to upload make correction in here and upload it. So with that, let us proceed to our next question, that we have two signal yt and zt, and we are supposed to find the convolution of them. By the way, this is not multiplication, this one here is convolution. So let's first write the standard convolution notation. We have xt and yt. The convolution is given as the integral minus infinity to infinity x tau y t minus tau d tau, that is its convolution. Now let's see what we are given. We are given z of minus t convolution with y star of minus t. Okay, so first consider this z of minus t as z tilde of t, and this one here y star of minus t, consider y tilde of t. So So then we are supposed to find the convolution between z tilde t and y tilde t. So let's try to find them. It will be given as minus infinity to infinity z tilde tau y tilde t minus tau d tau. Okay. Now we try to replace the function here. So z tilde of tau, this one is nothing but z of minus tau, and y tilde of t minus tau z of minus tau here, and y tilde of t minus tau is y star tau minus t, right? So we'll have minus infinity to infinity z of minus tau y star tau minus t d tau. Okay, this is being done. Z tilde t, let me check once whether I have done it correct or not. Tilde t here, tilde t minus tau. Okay, I guess here I did wrong, so it should be not tau minus t here. Here tau will remain minus only. T sign will change, it will be minus t minus tau. So this here should be minus t minus tau, and it's okay, this part is fine. minus t minus tau minus t minus tau here. Now I'd like to make a change of variable here. We are calling tau dash as minus tau. So then this integral limit will change. It will be now from infinity to minus infinity z of tau dash y star tau dash minus t, and here it will be d. Earlier it was d tau. Now I want to write it in terms of tau dash. It will be minus tau dash. So this minus here will flip, this minus here will flip the limit again, flip limit again. So what we are left with, the limit will again go back to minus infinity to infinity. We have z tau dash y star tau dash minus t d tau dash. Okay, fine. So let us see which one of them matching. uh, this is minus tau t minus t. No, it is not. Z tau dash minus t d tau. Okay, the second one is the correct answer for this. Okay, let us move to our next question, which says this is the signal sync function c sync bt as, and it is asked which of the Fourier transform it is going to have. So basically we are given c sync bt and what Fourier transform it is going to have. So let us first try to calculate it in a conventional manner, and then I will show you the trick to do it in few minutes, a few seconds maybe. So xt is given as c sync bt, right? So xf is going to be xt e to the power minus j 2 pi f t dt, right? Now let me write the sync function here in terms of complex sinusoid. So sync here is nothing but you will have c sine pi b t divided by pi b t. So we have already seen that pulse of duration t pt has this Fourier transform t sync f t, right? And using duality property of Fourier transform, we have b sync bt as pulse of bandwidth b. So from here only we can see that if we make this change here, now b sync pt has this Fourier domain frequency domain representation where p b of f in frequency domain is given by this pulse here of unit amplitude and bandwidth b. Now we are given c sync bt, right? So both side we multiply by c over b, c over b times b sync bt has the Fourier transform c over b p b f. So here we will have c sync bt, that is our uh, signal in consideration. Here we will have Fourier transform c over b frequency domain pulse of bandwidth b. So you can see for this one Fourier transform representation we have a frequency domain pulse of bandwidth b, but the amplitude is given by c over b. Now we use here the duality property of Fourier transform. If we try to go in conventional way, let's try that also. So we have c sync bt, that is c sin pi bt divided by pi bt. C over pi bt. I'm interested about sine function. I would plan to write is a difference of two complex sinusoid, that is e to the power j pi bt minus e to the power minus pi bt divided by 2j. And if we compute the Fourier transform of that, minus infinity to infinity xt e to the power minus j 2 pi ft dt. Now we have minus infinity to infinity c over 2j pi bt e to the power minus j 2 pi f minus b by 2 t and minus e to the power minus j 2 pi f plus b by 2 t dt. So minus infinity to infinity c over 2j pi bt Okay, there is one t here in the denominator. So this one here will take a lot of time. So that is why it's much easier to use the property of duality of Fourier transform to obtain the frequency domain representation of the signal, because if you proceed to compute the integration and all that, it will take a lot of time. Now this question is about okay, I think we have, okay, we didn't point it out here. It's the pulse with amplitude c over b with the bandwidth of b by total b. So this one is the answer. So basically we are given a Gaussian pulse here, gt, and e to the power minus 1 over 4 t square, and we are supposed to find the Fourier transform. Okay, now Fourier transform is given. Find gt is equal to gf by applying Fourier transform here, and we have obtained ddf, derivative of this Fourier transform capital G with respect to frequency produces alpha f g f. So we are supposed to find this value of this constant alpha. So how should we proceed? First let us check what happens when you take the derivative of Fourier transform with respect to frequency. For that we need to write the expression of gf, which is gt e to the power minus j 2 pi ft dt. Now if I take the derivative with respect to f, it's actually pretty simple, because the right hand side is a function of f, but the integral is with respect to t. So integral won't prevent us to compute the derivative here. So basically this term here is only function of f. So what we will have here, gt d df of e to the power minus j 2 pi ft dt, and what we will end up having is minus j 2 pi f will be common outside. Inside you will have gt, you will have t also, e to the power minus j 2 pi ft dt. So what this term represent? So this is basically minus j 2 pi f times Fourier transform of t g t, right? So we keep it as equation 1, that when we compute the derivative of gf with respect to frequency, we obtain some constant times Fourier transform of tgt. Now we focus on what happens when first we take the derivative of gt. So what we will obtain? d dt of gt. We will basically have minus 1 over 4 2t e to the power minus 1 over 4 t square, right? So this one here is nothing but minus t by 2 gt, or we can say minus half tgt. So we have this equation 2. Now let us see what happens when you compute the Fourier transform of this. Okay, we have gt, which is given as just a moment, think ddt of gt. Okay, gt can be written as gf e to the power j 2 pi f t df minus infinity to infinity. So when we take the derivative with respect to t here, what we will end up obtaining is 2 pi f minus infinity to infinity gf e to the power j 2 pi ft. Let me write it in the next page. So what we already have is um, d df of gf. We have already obtained. This is nothing but minus j 2 pi minus j 2 pi minus j 2 pi f Fourier transform of t gt, where gt Fourier transform is given as gf, and we have that d dt of gt is nothing but minus half t gt. Okay, so therefore that means t gt minus t gt is equal to 2 times d dt of gt, and therefore Fourier transform of minus t gt is equal to 2 times Fourier transform of d dt of gt. and if gt has Fourier transform gf, what is the Fourier transform of ddt of gt? It's nothing but j 2 pi f g f. So this is equation 1, this is equation 2, this is equation 3 here. So what do you obtain here? That d df gf is nothing but minus j 2 pi f. Fourier transform of tgt is nothing but 2 times Fourier transform of this, and this is given as j 2 pi f, 2 j 2 pi f, 1 j involved here. So it would be minus j square, that is 1 8 pi f square gf gf. So this is the constant we are looking for. This constant is what should be the constant? Oh, here is 2 pi 1 pi 1 okay, it's 8 pi square, sorry. This one here is 8 pi square f g f. So this constant that we are looking for should be 8 pi square. Gt 2 pi f. Okay, sorry, I made a mistake here, small one, that there should not be f any here. J 2 pi ft, we are taking derivative with respect to f, so 2 pi t only, so okay, sorry, should be 2 pi here. So okay, there should not be f here and no f here, so yeah, now you will have 8 pi square f gf. Okay, fine. So this is the constants we are looking for, and this is what we are obtained here, 8 pi square. With that, let us move to our next question. That says if xif denote the Fourier transform of this, then what should be the this integral? Okay, so first we need to see what happens when x1 t okay t dt. Okay, let's try to find similarity to this. What it represents, this is x1 t x2 star minus t dt, right? So let us first try to find the Fourier transform. See, Fourier transform of x2 of t is given, that is x2f. I am interested to find the Fourier transform of x2 star of t. So how can I do that? So for that, let me write the x2f, how we calculate it. It's x2 t to the power minus j 2 pi ft dt, right? Now I have x2 star of t. So how should I proceed here? So let's take conjugate on both side here. X2 star f is equal to x2 star t. This side will have conjugate, so 2 pi ft dt. Okay. Now I need to make a change of variable. We say f dash is equal to minus f. So x2 star is equal to minus f dash here, integral x2 star t e to the power minus j 2 pi f dash t dt. So this right hand side is the Fourier transform of x2 star t, and what is the expression for that we are obtaining? F is equal to f star, f is equal to minus f star. So Fourier transform of x2 star t is x2 star minus f. Okay. Now with that, let us compute this one here, minus infinity to infinity x1 t x2 star tau minus t dt. So what is this thing here? It is basically the autocorrelation between x1 and x2 star. So rx tau, if I need to write in terms of the frequency spectra, what it's going to be, minus infinity to infinity x1 Fourier transform of that is given as x1 of f, x2 star, what is Fourier transform is given as x2 star minus f, and e to the power j 2 pi f tau df. So basically these two are equal. Now if I say tau is equal to 0, so let's say this is equation 1 and this one is equation 2. Now what I am doing is setting tau is equal to 0. Now when you set tau is equal to 0, here what you are left with is minus infinity to infinity x1 t x1 t x2 star minus t dt. On right hand side you will have this tau here is 0, so basically you are left with minus infinity to infinity x1 f. Now second term is very crucial, we have x2 star minus f. Okay, x2 star minus f df. So from this expression we can see this matches with the left hand side, and right hand side should be x1f x2 star minus f, x1f x2 star minus, this one should be the correct answer. Now let us consider the Fourier transform of the signal. This is again a pulse signal in time domain, uniform amplitude and absolute value t. Okay, this one is from minus t to t, so total time domain is 2t, where the signal is non-zero and 0 outside. So what should be the Fourier transform of that? Now we have already seen that for a standard pulse signal, here that runs from minus t by 2 to 2 by 2, so this is uniform amplitude, so this we call as p t by 2 t, and this has a Fourier transform of t sinc f t. Now similarly for this, what we will get here, just we need to replace t by 2 with t. So what will happen here is like this. This is p 2t, sorry, pt here of t. We'll have following Fourier transform. T will be replaced by 2t, and it will be sinc 2 ft, and what result it's going to produce? 2t sinc 2 ft will be nothing but 2t sine 2 pi ft divided by 2 pi ft. So this 2t will cancel here. We'll have sine 2 pi ft divided by pi f. So we'll have the third one as our correct answer. Now let me try the one which I could not do it. Where was that? Okay, this one here. So what I was doing, okay, so you have any question for me till this session, whatever I have explained? Anything you have difficulty in understanding, or something I should explain in a better detail? Because if you have any question, now is a good time to ask, otherwise I will conclude this session. I will correct the ones I made mistake, this one, and I will upload it into the folder. I think you already have access to that. Okay, if you don't have any question, then we can conclude the session. uh, Thank you for being here with me. We'll meet again next week.